Thanks for the introduction. Thanks for the opportunity to speak. I hope that the volume and everything is okay. If not, please let me know. So what I want to do today is report on some ongoing and past work. This is a mix of 3 different articles, and only one of them is written yet. And so it's a mix of works with joined with Jakub Jagiela, Mateusz Michałek, Piotr Osiel, Tim Senaf, and Colin Stasny. So I will be talking about flattening methods for lower bounding border rank. So let me start by just establishing some notation and conventions very quickly. So I'll be working mostly with 3 factor tensors. There will be in product of 3 vector spaces, A, B, C. Let's say everything is over the complex numbers. I will implicitly be thinking about this action of the product of the 3 GL groups. Next, the rank is, of course, the least number of terms, of simple terms I need to express my tensor in a sum. Then the border rank is sort of, I add a limit to this definition. So it's the least number of terms I need to limit to my tensor. Next, an important class of examples that I will be using will be structured tensors of algebras. So whenever I have a C algebra, let's say finite dimensional, I can encode its multiplication table as a tensor, and it lives in R dual R dual R, and it's implicitly given by this bilinear map multiplication. In particular, there's the algebra of D by D matrices, so I will denote its structure tensor as MMD. This is the matrix multiplication tensor. And towards the end, I will also slightly more generally be considering structure tensors of modules. So now I have an algebra, a module over it. Both are finite dimensional as vector spaces. And the action of the algebra on the module is again given by a sort of multiplication tensor, multiplication table, which gives me a tensor. Right. Next, there was the word flattening in my title, so I should explain that. For me, I will be considering flattening to be something as follows. So essentially, I want to turn my tensor into a matrix, and I want to have some nice adjectives on this process. So I want this to be a polynomial map to some space of matrices, and I want this to respect the G action. So I want to have this G action on my spaces as well. Any map like this, I will call a flattening. And then the crucial property I will use is the fact that matrix rank is lower semi-continuous. So if I move in the space of matrices, in the limit, the rank could only drop down. It will never jump up. And hence, here's like the very general blueprint of a flattening method. I pick a flattening, and I will pick a tensor. I want to lower bound border rank of this tensor, which is usually pretty hard. And I will pick a general tensor of a given rank. So I will, let's say, sample randomly from a secant variety, and I will compare the ranks of flattenings that my tensor gets versus this generic rank R tensor gets. And because of this lower semi-continuity, and I demanded that my flattenings are continuous in the Zariski topology because of the polynomiality, then I know that if I happen to find any one flattening where my tensor beats the generic rank R tensor, then my tensor must have had strictly larger border rank than R. Okay? And here are some examples. The simplest one, if you look in some places in literature, this people might just mean specifically this when they say flattening. I can just turn my tensor into a matrix like this by just forgetting that like these 2 vector spaces, this product of vector spaces was indeed a product. I just remember that it was a vector space itself, this A times B, and then this plugging in of two of the parameters, leaving the third one implicit. That's a flattening. And of course, if you work in bases, this is like chopping up my cube of numbers, my cube array of numbers into slices, and then just putting them on top of each other or next to each other. And I want to keep track of how good this is for low bounding border rank. So if I assume for simplicity that all my spaces have dimension n, then this is an n squared times n matrix. And so in principle, I could prove border rank at least n, which is not so great because the rank 1 tensor contributes with rank 1 into the matrix. Slightly more complicatedly, there are what's called coastal flattenings. Now I flatten into a more complicated space. And what you should imagine is that I take in a wedge product of two forms and the form on B. And in each case, I want to keep one of the alphas and pair the second alpha with the beta. But because of this wedge, I have to do it in two ways and put in a sign. And this turns out that this is a matrix. Let's write down the sizes. This is the matrix of sizes n choose 2 times n times n squared. And it's an easy exercise that rank 1 tensors become rank at most n minus 1 matrices. So indeed, this means that I have a little bit of space because the rank n tensor should only get rank n squared minus n. But indeed, the size of the matrix is such that I could go up to n squared. So this, for example, would allow me to prove border rank at least n plus 1. And this is, of course, a very baby example, because what people do in practice is they apply a random projection on the space that I'm wedging, and this turns out to be beneficial. So then people can get to around 3/2 n. Right. So those are my examples. Now I want to talk about a phenomenon that motivated some of these methods that I want to talk about, and that's the so-called cactus barrier. And this is sort of a limitation of flattening methods that we wanted to overcome and that we indeed managed to overcome. And for this, I need to define cactus rank. So let me restate the definition of rank in like a needlessly scheme theoretic language. So let me call X the Segre variety in the projectivization of my tensor space, and then the definition of rank. If you ask if you ask Grothendieck, let's say, he would say that this is the minimal degree of a smooth zero-dimensional scheme embedded into the Segre variety, such that your tensor lies in its span. And well, then there's a conspicuous word, smooth. Well, cactus rank is what I get if I just drop this word. So cactus rank is the minimal degree of any scheme to embed inside the Segre variety, such that I catch my tensor in the linear span. And this is, at least I feel this is very counterintuitive, but somehow there is a very big richness of zero-dimensional schemes. So usually when we allow all of these schemes, we can manage with much smaller degree. That's the idea. And something I will need, which I want to state as a fact, is that if I take a structure tensor of a Gorenstein algebra, then these are known to have as small a cactus rank as possible, because there is actually a way to embed spec R, so the zero-dimensional scheme given by this algebra itself, into the Segre, such that the structure tensor lies in the linear span, so that there is this sort of like a tautological statement about this. Sorry? I'm talking about cactus. I'm talking about cactus, yeah. Sorry? That's the structure tensor of the algebra. So that's given by the bilinear map A tensor B goes to A times B. And so similar to usual rank and border rank, I define a border version by allowing closure. And so the behavior that we get in general is that there is this square of inequalities, but in general it might be hard to compare these opposite vertices, the border rank and cactus rank. But intuitively, what you should be thinking is that cactus rank is usually pretty small compared to border rank. And so now the idea, sorry? X is the Segre. Yeah. Sorry, I'm abusing notation a bit. I'm imagining that for my structure tensor, A and B are R dual and C is R. So now the problem of the cactus barrier goes like this. People have been observing that these flattening methods that they know seem to, for some reason, not just be lower bounding border rank, which we usually set out to do, but they seem to be lower bounding border cactus rank without intending it. But by some naive dimension counting, if I look at a product of 3 n-dimensional spaces, then border rank should generically go to about n squared over 3. We have the exact number. I just care about the asymptotics. But border cactus rank only up to roughly 6n. So this is why I say that border cactus rank is usually much, much smaller. And somehow the conclusion of these two statements means that this should be a thing that makes flattening methods bad, or at least not very effective. Because I want to be lower bounding something, but I'm secretly forced to lower bound a different thing, which happens to be much, much smaller. And that's bad for me. And recently, sort of like a more formalized statement of this problem that is present in, I think, the thesis of Gałązka and in a recent paper of Buczynski, is this: if I have a linear flattening F, and I say that it maps decomposable tensors to matrices of rank M, so this is the rank on the Segre variety, then if I look at tensors of border cactus rank up to R, it will only give me matrices of rank up to M times R, which is indeed the rank that R times R identity tensor, that's what I mean by this IR, should get. So this is like a formalized statement that's telling me I cannot succeed if I have low border cactus rank in lower bounding border rank. So like a very distilled version of the cactus barrier posed as a challenge, as like a thrown gauntlet, is this: cactus barrier says that I shouldn't be able to prove of a Gorenstein algebra that its structure tensor has bigger border rank than the dimension of the algebra. If I'm to believe that the cactus barrier exists, this shouldn't be possible. And in the remainder of my talk, I will tell you that I can indeed do this, so we can break the cactus barrier. Right. And there are these two conspicuous words, linear and flattening. Somehow, maybe like if you remember one thing from this talk, I would like you to remember that flattening is not the source of the barrier. The linearity is the source of the barrier. So if we go to higher degree flattenings, we can break it. So let me explain the construction that we will use. This is something we ended up calling Kronecker Kossel flattenings because we think it generalizes the Kossel flattenings. It just puts in front Kronecker power. So I want to be building a polynomial map that turns a tensor into a matrix. And well, if I'm building a polynomial, I might as well start with the Veronese map. That's the universal thing. And on tensors, I can present the Veronese as just the tensor power. Maybe this is some redundancy because maybe I have some monomials that are present multiple times in the coordinates of the tensor, but this will still have the universality that's any polynomial now I can create as just a linear projection from this tensor power. And I want to think about rank decompositions. So I prepared one on the table on the blackboard, and if I have a tensor that looks like this, so it has a length R decomposition, then I could just tensor this whole decomposition by some sort of a non-commutative binomial theorem, and I will get a decomposition of length R to the D. So this gives me immediately a bound on the rank of the power. But the trick is that this is not just any old decomposition of this length. It has a very special structure because there are some very special terms. So let me write an example. Here, if I take a tensor power, I have a. Sorry, is there a problem?
Keep going.
Okay.
Keep going.
Okay, I'll keep going then. What I want you to notice that among these R squared terms, there are the ones where I and J happen to be the same. And then I have a repetition. I have AI, BI, CI. And I can now choose projections from this tensor power, let's say from this space A to the D tensor power or B to the D tensor power. I can choose projections that will eliminate these special terms with repetitions. So the blueprint of the method is this. I start with the tensor power, and just like in Kossels, I could tensor in a bunch of identity maps on these either on these spaces A, B, C, or even on their exterior powers. So I will in general get a very high order tensor, but most of these are like some powers or exterior powers of A, B, or C. Then there's some duals maybe. And I could choose to take some of these factors and contract them further. So maybe I could choose an A squared and contract it to wedge 2A. Or I could choose an A squared and wedge 2A and contract them all together into a wedge 4A, right? And this will eliminate terms with repetitions because A, which A just vanishes. And so let me actually jump straight into our, I would say, our most successful example, and that's what we call a tangency flattening. Now, let me let the name be a bit of a mystery for a while, and I will come back to it later. But this comes about by taking the second tensor power and tensoring within an identity on A. So on this level, I should have that T twice tensored with A is something like sum over ij from 1 to r of AI, AJ, BI, BJ, CI, CJ, and then identity on A, which let me just not expand it for a bit. Now, when I wedge those 3 copies in A, so I should write that this lives in A tensor 3 times, B tensor 2 times, C tensor 2 times, and then there is a copy of A dual that's coming from the identity path. Now, if I wedge these 3 to a third wedge power, I will surely kill all of the terms where I and j happen to be the same. So I will have r times r minus 1 many terms, including this id. So let me actually move this one further. I claim that I can bound, if I know the border rank of the original tensor, I can bound the rank of this matrix. So if I turn it around, if I start with the tensor, I build the flattening, I measure the true rank, and if it happens to be more than this bound, it gives me a lower bound on the border rank. And so I said that I already have this r times r minus 1. That's the number of terms that survive this projection. Now I just need to say that this identity A, which usually would be a rank n tensor, it's a rank n matrix, full rank. Under this projection, I can actually drop it to rank n minus 2, because anytime I choose a basis of A, so let's say U1 up to UN basis of A, then I can write it A with the decomposition UI tensor U1 dual, where I chose the dual basis of A dual, plus, etc. UN tensor UN dual. So my trick now is that I can choose many different decompositions of this id. And so now if I look at one term with ij distinct, this means that this term survives. So AI, AJ are linearly independent. So I can extend them to a basis. And so if I take this decomposition of id r, there are n terms, but 2 of them have either AI or AJ. So they also disappear in the wedge. So that's how I get this bound. So sorry, you're asking where this lives?
It's a name of this tensor A star so A.
Yes. Yes. Which is like endomorphism.
Then I has 3 copies in A. Like it's a tensor 3 times.
Yes, okay.
Yeah. So in the end, when I apply this contraction, I should end up in here in wedge 3A, tensor B 2 times, tensor C 2 times, tensor B star. So this is a 1 plus 2 is 3 plus 2 is 5 plus 1 is 1. So order 6 tensor. And I will just now choose a classical flattening of it. And that's the one I wrote. There's a bit of a choice about which B and which goes to the left and to the right, but I do it in the interesting way. So the 2 copies go in opposite ways. And so now I have this bound, and now I will do things with it. Namely, I will show you an example of breaking the cactus barrier. I will pick R to be the polar algebra to a generic cubic in 6 variables. So this is like a general local algebra of Hilbert function 1661. This is very famously known to be what's called non-smoothable. So it has border rank bigger. The structure tensor has border rank bigger than its dimension. but we can actually verify it with a flattening, because when we just on a computer build this flattening, we get that the rank is 2,192, which is 8 more than what this formula would predict if the border rank was indeed n. So this proves non-minimal border rank, even though by the theory I asked you to believe for a fact, this does have minimal cactus rank. So we have indeed separated the two. So already, so as a function of the tensor, this is a quadratic map. So we're already in degree 2. Once we upgraded from linear flattenings, we were able to break this. Next nice result that we sort of stumble upon is a new proof that the border rank of matrix multiplication 2 by 2 is 7. This has been known for a while, but I think all of the proofs involve some heavy machinery or even like a lot of computer assisted case checking and such. So if we plug in MM2 into our tangency flattening, then by plugging into this formula, you can see that if the border rank was at most 6, so by this sigma 6, I mean the secant variety, we would get 6 times 5 times 2, which is 60. But when you write it down, this is a full rank 64 by 64 matrix. So this proof is almost like a linear algebra exercise. So that's the tangency flattening. Now, let me mention another example. What we can do is, I'm slightly cheating because I said I will only use wedges, but now we'll also use symmetric powers. I could create something like this. So this involves no identities. This is just a pure power, tensor power of the tensor. And I project it to a wedge on A's, a wedge on B's, and a sim on C's. And this is a very nice elementary interpretation, because I could look at C as a matrix whose entries are vectors from C, right? That's a way to view a tensor. And then the image of this matrix is just the space spanned by minors. So again, something relatively elementary. And if I'm, again, playing this game of comparing myself with like an identity tensor or a generic tensor of some given rank, then it's pretty easy to see that if I take an identity tensor, then this matrix is just a diagonal matrix and distinct variables on each entry. So then this just measures the space spanned by square free monomials. So it's just a binomial. So it's all very, very, very manageable. And then we can cook up another example where we take an polar algebra to a cubic in 8 variables. And there again, we can win with this, proving non-smoothability. And I would like to stress that this is I think, interesting, because in the field of studying this border rank of algebras or non-smoothability, what's called Hilbert schemes, I think this is considered to be hard to handle, because this algebra as a point in the Hilbert scheme, it lies on a large dimensional component, and I've been told by experts that this is considered to be a problem. So I think we understand this phenomenon slightly less, but at least it's a proof of concept that these tools could give us something. And then there's a generalization where we can go through representation theoretic machinery, and we can play this game with a different choice of Weil modules. So instead of going to wedges and sims, we could just pick any 3 of our favorite partitions. Maybe in the interest of time, I will skip this. Lastly, I want to mention, I want to pay a debt. I want to justify the name tangency flattening. And this leads me to some connections to some homological and geometric data. So let me introduce one last thing. This is the mixed tangency flattening. It's essentially just like the tangency flattening, but instead of taking a second tensor power of a tensor, I just say that there were actually 2 distinct tensors and I tensor them together. The only thing I demand is that they share the first space, the first factor of where they live, because otherwise, the wedging wouldn't even make sense. And then what I will do, I will start plugging in structure tensors of modules over an algebra. So this fits this condition because their first factor for modules over R, the first factor is R dual. So this is legal. Yeah, thanks. And then we can prove that this mixed tangency flattening somehow indirectly measures some homological data, like the hom space over the algebra and the X module but there's a bit of technicality where it's a X module over a polynomial ring that I use to present my algebra. So it is slightly complicated, but the place this is going is that if I put A and B both to be just the algebra itself, then it is, I think, pretty well known in the literature that this X is a particular presentation of the tangent space to the Hilbert scheme. So then we get that in this indirect way, the tangency flattening measures the size of the tangent space to the Hilbert scheme. So that's the motivation of this name. We originally just observed this numerically, and recently, with the help of some colleagues from Warsaw, I think this is now proven. And I think I'm running out of time. So very last, let me just very quickly say the last few results. We also have a connection to tangent spaces to the scheme of commuting matrices, which can be seen as a thing that parameterizes modules. And we can also do some homological shenanigans where I switch one module for its dual, and by some duality, instead of X modules, I can measure torus. And if I go back to algebras, this again has some relatively easy algebraic interpretation. And what I just want to say is that this is also a useful criterion for non-smoothability of algebras. We have some examples where this can prove non-minimal border rank of an algebra, even though, for example, the tangent space method fails. So we have again these proofs of concept that this could be useful. And I'm already over time. I'm so sorry. Thank you.
Are there any questions?
We're also happy to talk over coffee.
There are the numbers. Would you have an interpretation of the kernel?
You mean in general, or for these examples like tangents? So for the tangency flattening, I wouldn't say we have the interpretation of the kernel, but we have actually the proof of this proposition goes by looking at the kernel of the dual map. So maybe it's I don't know, maybe it's a bit of a lie for me to present it this way, because then the proof of propositions like this goes through interpreting the kernel of the dual map. So something inside A tensor C1 dual tensor B2 dual. For the interpretation, maybe let me specialize to the case where A and B are the same module, and then this kernel of the dual map is it's the tangent space to the commuting matrices plus, I think, something trivial like plus the endomorphism ring over the vector space. So somehow it splits into the kernel splits as a direct sum of this tangent space plus something that's very uninteresting. That just depends on the dimension. So in general, I think we don't know. I think we would be very happy to know, but I don't think we do. We only have these interpretation in some select cases and only when plugging in these structure tensors. I don't think we have anything in general for a tensor that doesn't have algebraic interpretation. Sorry. Which one? This? You mean the first one on the slide, or? This?
Yeah.
So I basically did it on the blackboard. It's just I look at the decomposition, I exploit this special form, and I justify. So naively, I should have a decomposition that's of length r squared times n. So I just need to like kill a few of the terms by the projection, and so this is justified by saying that first I kill the repetitions, and then I slightly more subtly have to kill some terms in this id, where I have to choose a different presentation each time, but.
Okay.
It's relatively elementary.
The example that you have here, like on the
Yes.
to the 1661. Right?
Yes.
So your minors, so how do they relate to the ideal of the, are they sufficient to generate the ideal of that non-global scheme, or do you need something more?
I don't think we know. I think we have no idea. I would intuitively I would expect that they are not everything. That would surprise me, but I would say the true answer is we have no idea. And since you mentioned mine,
All right.
these are very big minors. These are like around size 2000 degree polynomials in 14 cubed variables. So, yeah. But since you mentioned minors, something I forgot to say and I forgot to put in my slides. So if we put in Gorenstein algebra specifically, then we also know that 3x3 minors also measure the tangent space sort of indirectly. So for Gorenstein specifically, we have this relation between the tangent flattenings and the 3x3 minors flattening. Thanks for reminding me. But yeah, I think it would be very interesting to know, but I don't think we do.
So here you show these two examples, like this example and then the one for
881. Yeah.
And they're kind of two different patterns. Like, they're not the same flattening.
Yes. This is a tangency, or I could equivalently use the 3x3 minors, and there I had 4x4 minors.
I'm thinking, like, if I look at generic tensors for the rank n+1.
Yeah.
We know that the first the Kosovo flattening will give bounds on generic tensor. Like if I pick the generic algebra for one NN1, one KK1, do you have like a candidate flattening that would work?
No, we don't. So the 3x3 minors are tangency. If I go with higher 1kk1, that of course stops working, because I think this is pretty well known that the tangent spaces, they become big. So somehow this 161 is an anomaly.
161 is small.
Yeah, it is small. Yeah. We win if the tangent space is small.
But then you are in this big component.
Yeah. So the 3x3 minors or the tangency, they don't win. I think we checked just on examples that 1881 4x4 minors win. I think on 1991 we checked 5 minors, but we certainly don't have any general statements. I don't know if going to higher minors might be the solution, but of course it becomes very impossible to check on a computer very quickly.
So we shall move without further questions to the coffee break. And thanks for.
Thanks again.
That